All right, it is the top of the hour on a hot, hot day here in Minnesota. Welcome to our regular webinar series. I'm James Okula, the Director of System Planning at ESIG, a membership-based nonprofit organization committed to providing our members with objective information, resources, networking opportunities in support of the energy transition. We do this a number of ways through workshops, tutorials, webinars, blogs, working groups, task force activities, and producing technical resource materials. Our workshops and webinars are open to everyone, so please feel free to register anytime on the ESIG website. Now, if you're new to ESIG, I strongly encourage you to follow up with us if you'd like to know more about what we do, and I think you'll like what you see and what you hear. You can find us on the web at www.esig.energy, as well as on LinkedIn, Facebook, our YouTube page, and X. Our next in-person workshop, which is open to the public, will be June 24th through 27th in Nashville, Tennessee, and that is focusing on forecasting and markets. The last 2 days, day and a half really, will be our next workshop on large loads, primarily focusing on resource adequacy in markets. Now, this portion of the workshop is open to only ESIG members, and so if you're interested in ESIG membership, please reach out to us. Again, for more information, please go to our website, esig.energy, under events, and that will give you a full listing of all the events that we're offering. So before we jump in, let's go over a couple of logistics. Please note that to avoid distractions through the webinar, participant lines have been muted. So for Q&A, we'll be using Slido. So go to slido.com. That is SLIDO.com, and enter ESIG12, ESIG12 as the event code. The instructions are also going to be at the bottom of the screen here, so you can use that to get to the Q&A section. We will leave 10 to 15 minutes at the end, and we will wrap up promptly at the top of the hour. And lastly, an email with a link to the video will be posted shortly after the webinar and all the questions have been addressed. So let's jump into the topic of the day. So we're focusing on one of the most pressing challenges in the industry today, and that is accelerating the generation interconnection process. Now, generation interconnection is the formal process through which new resources are reviewed and connected to the transmission system. It's a critical gatekeeper for bringing new generation online, ensuring that projects do not compromise system reliability and that needed transmission upgrades are identified and funded. But this process is under strain and has been for some time. A recent that I think should be updated here fairly soon study from the Berkeley lab shows that there's over 11,500 active projects seeking interconnection across the queue, and that's a total of 2.6 terawatts, and that's about double the amount of installed capacity at the moment. The study also notes that there were 17,800 projects that entered the queue but withdrew. Now, MISO has experienced some of the same pressure. As of March 2025, there was almost 1,600 projects active in MISO's queue, and that's about 300 gigawatts, and that's far, far exceeding the peak demand in MISO. And study cycles are quite often delayed, currently taking 3 to 4 years to complete, with late-stage dropouts triggering studies and further delays. And that's why MISO has set out the goal to reduce the queue process time to 1 year, and automation is a key component of that. And that's what we're going to be hearing about today. So about our speakers, Ryan Westphal is a senior manager for resource utilization at MISO, where among other things, he manages the integration of new generation resource into the MISO system. He has been with MISO for over 15 years in a range of planning and policy roles and holds a Bachelor of Science in Electrical Engineering from the University of Minnesota. David Bromberg is co-founder of Pearl Street Technologies and now the VP of Power and Renewables at Enverus. He led the development of sugar from its research roots at Carnegie Mellon to its current deployment across the industry, and he holds a PhD in electrical and computer engineering. Once again, please use Slido with the event code ESIG12 to ask your questions. Again, thank you so much for joining us, and thank you to our speakers for taking the time to speak on this very important and pressing topic. I will turn it over to you both now.
Well, thanks, James. This is Ryan Westphal. I'm going to start the presentation, and thanks for that introduction there. And thanks again for the invite for this webinar. It's a very exciting time here at MISO. We've got a lot of things going on. We've implemented quite a few reforms, and now we've got some technology that we really are hopeful for to really speed up the queue process. So we've been working over the last about 6 months or more, kind of integrating this process into the MISO interconnection world. And so, we've had some very good success, some benchmarking we'll go over a little bit on there. And then also, some of the 2022 cycle work that's been ongoing now. And we've even got future things we're working on for the future cycle. So again, very excited to kind of highlight some of this work and talk through some of what we've done and kind of highlight some of the future for that. So thanks again, James, for the invite for this webinar. And so, as James rightly illustrated at the beginning, we've got at MISO we're challenged right with the queue volume, and we've got a backlog of applications that are contributing to delays of resource additions. Right, a couple years ago, we basically made a tariff change that we wanted this process from interconnection application to signing a GIA in 1 year. And so we've had that in the tariff for several years now, but unfortunately we haven't been able to achieve that yet, right? We've had cycles taking about 3 and 4 years. They've been challenged by late stage dropouts from some of the recent queues. And then even generation increments, are being challenged in the next 3 to 5 years. And so, again, I think everybody's kind of seen this, right? That we've got a large backlog of queue, 300 gigawatts here in just these 3 active cycles, with another one in 2025 that's going to be ending up closing the next cycle here at the end of this year. And so we've got a big backlog. And so, that's been the challenge that we've had for quite a few years. And so getting some of the things that we've done here recently into improvements. We've done some reforms recently to help with some managing of that. But also we've had the Order 2023 compliance that FERC had introduced, which, our process was quite in line with that 2023 process. Of course, there are some things that we did have to work through on that order compliance, but fundamentally very close to what that Order 2023 compliance is, what MISO kind of already had in place. We had some JTIC work that's accomplished and is continuing to, in the future, going to help with some of the interconnection. So we've got all that accomplished in the last year and the years prior. Most recently we had a queue cap approval that is helping with the queue improvements, and then finally some other processes in terms of tracking of commercial operation dates and the like, that is helping bring some transparency out to some of the resources and the GIAs that we have available and ready after going through the queue process. So again, what we've got here is we've got a lot of accomplishment, but those are helping a lot more, I would say, into the future cycles, right? CAP is in the 2025 cycle. A couple of these other reforms weren't starting until the 2023 cycle, and et cetera, et cetera. And so this software innovation that we're going to talk about today with Sugar is a huge part of managing this and getting through this backlog. 2022 is basically the cycle that I would say has started it all, right? We had the 170 gigawatts that started it. We're down to about 140 now that we're studying currently in the 2022 cycle, and this Sugar is being used to help us get through that first phase of that 2022 cycle. And so been implementing quite a few things here over the years, and overall, we think it's going to take a couple of years, several years to get down to that 1 year time frame. But a lot of these things, once they start getting implemented and rocking and rolling, and in particular the software improvements and innovation with this, is going to be a huge part of meeting that 1 year timeline. So what are we automating? What are the interconnection studies, and how is this all working, right? So I'm going to start at kind of like a pretty high level and let David in the next couple slides after just kind of go into a little bit of the details under the hood per se of the Sugar process. And so, if you look at this, there's a ton of different boxes here, and there's probably even more than this. It's at the end of the day, the process, while overall, is seemingly simple. There's a lot of intricacies here and a lot of things feeding into each other here, right? One of the things, right, we've got the database with all the data for all the generation and all the new resources. You've got to actually model those in a power flow, dispatch them, got to run it. And you go through all these steps and throughout to basically get you from the interconnection request back to producing results, right? There's a lot of different steps here. And one of the challenges that we've struggled with for a while at MISO and others too is many of these steps are very manual still at this standpoint, right? Getting spreadsheets, checking data, kind of the way more manual process than we really need and really want, right? We want a lot of automation here that can get the data we've got this tool, right, that has all the application data. Can we get that, build the model, and run all this stuff much more seamlessly and error-free and error-prone? Can get rid of those errors a lot easier than we do when you're doing it manually, right? And when you look at all of these steps, one of the biggest time sinks, and that's what we'll kind of talk about here in the next couple slides, is the building and dispatching of power flows, right? You've got all these generators, and basically, they've requested a point of interconnection onto the transmission system. Well, that's great, but then you got to actually put it in the power flow, make sure it works. There's a whole host of that goes around that, and that's pretty manual at this point, right? Taking it, putting it in, checking and whatnot. And so that's a big part of the time. And particularly when you have cycles as big as that we had in the 22, when you have 1,000 generators, it takes a lot of time and it's manual. The next, probably most important piece that we worked on for the 2022 cycle, late last year, early this year, is you can build the model. It's all well and good. It's pretty manual, and you can run the power flow and you get all the constraints, right? You see here, those are only two blue, right? You push the button, you get the constraints, and the model tells you, well, these are the constraints, right? The next steps really are, well, how do you fix these constraints, right? And so a lot of that is very manual at this point too, right? Like I can, there's many different options that can exist to fix those constraints. For example, new conductor sizing, et cetera, et cetera. And so what we did for our process, and a little bit, we'll get into a little bit of details, is we created basically a rule set that we could automate to get those mitigations, right? And so basically the tool is making those decisions on those constraints and how to fix them, based on criteria and rule set that we created with our MISO stakeholders and implemented that. So, in addition to identifying those constraints, you also have to put a cost to them. And so a good thing for us, we had another document that had been actually worked on and produced over the last couple of years and gets annually updated, is basically what we call a cost estimator guide. And so when you put those two together, that's where a lot of the work, at least to date, has been done on, is basically automating that piece of the puzzle, right? Is you got the constraints, I need to fix those constraints, and I need to do them quickly. And so we've automated that and have put together the kind of the documentation white paper that kind of explains how we've done that. And as part of all of that, these are all iterative. And so there's, you plug them in, you got to make sure those mitigations work. And, with the amount of projects that we have, this iterative process can take a while, right, to get down to the point of, here's the mitigations that are good for those constraints, and ultimately those are put into a draft form for our customers to look at and essentially look at them and see if they are appropriate, or even provide alternatives to those mitigation. So that's a big part of this, is still the feedback that we get from our customers on that. So we get these answers really quick based off of our white paper, our iterative method, and then, right, you can basically look at the solve case, with mitigations, and make decisions that some of these look okay, some of them don't. And ultimately that's where we're getting a lot of feedback is, hey, these alternative mitigations may be better, and we can test all those. So that's a big piece of all this, and we'll talk about ultimately there's a final say if there's an upgrade that's not going to work because, hey, your tool didn't know there was a river here between these two towers. Well, that might not be so appropriate, right? We don't know there's a river there at this point. So, those kind of feedback will help on kind of getting those mitigations to a point that we're comfortable at. So that's kind of the overall part, like where we're focusing at least a lot of the time today. Um, in the future, and you'll see in our later cycles, the model building piece is going to be a big piece of what you'll see in the automation that's speeding up a lot of the process. Today, the 2022 model was basically, the 2022 cycle had already been built, so it really didn't need a model building aspect of it at this point. But we'll see some of the fruits of that labor here in the future cycles on that model building aspect. So I'm going to turn it over to David now, and he's going to go through some of the more intricate deployment details of the Sugar software tool.
All right. Well, thanks, Ryan, and thanks, ESIG, for having us. I've actually always wanted to give one of these webinars, but I've always found the topics to be very sophisticated, and I've never felt qualified. So I'm just going to try not to sound too dumb here. But building off of where Ryan left off in regards to the deployment of our software at MISO, we were kind of dropped in from a helicopter to a study that's already been in flight with the 2022 cycle. This table is basically lifted from a recent IPWG Interconnection Process Working Group meeting, highlighting a planned rollout of our software's capabilities. So to Ryan's point, for the 2022 cycle, the foundational study models had already been built. They've been updated and modified since they were originally posted a couple years ago, but we didn't have to start there. We really came in to polish off the analysis and then the selection of upgrades, validation that they alleviate constraints, estimating the costs, and creating a final report. And additional complexity with the 2022 cycle is that partial results have been available. So, we worked off of those. It was a lot of moving pieces for sure. With the 2023 cycle, which is scheduled to kick off later this summer, as Ryan said, we'll kind of be starting from scratch, building the power flow models that underlie the study based on kind of the MTEP, the transmission planning models, as well as the interconnection request data. So on the fly, adding those on top of the MTEP model and creating the study models for the interconnection study, and then performing all the analysis. For the 2025 cycle and beyond, we're working with MISO to integrate some capabilities into the interconnection request submission system to help QA projects as they are submitted into the queue, so that we could be more confident once the study kicks off that all the projects are basically ready to go for inclusion within a power flow study. And this is all very high level. There are likely 1,000 different things we could have added onto the slide, and certainly a lot that we're always in talks about for improving for the future, as well as incorporating feedback as we receive it from 2022, 2023, and beyond. So just kind of tying this with the flow chart that Ryan was just going through a couple slides ago, this is also lifted from one of Ryan's masterful IPWG presentations. But to give you an idea of what the system actually is, we call it Sugar, which is sometimes a little bit confusing in that we also often refer to Sugar as like a power flow engine. But there's certainly a lot that's involved in this system in terms of data intake, data versioning, orchestration of computation, the computation itself, and then report building. It all starts with creating the power flow models, or in the case of the 2022 cycle, taking in the models that had already been created by MISO, performing the power flow analysis, which comprises a DC analysis, basically like a DC screen, followed by AC verification, determining upgrades like Ryan indicated. We'll have another slide or two about that, as well as estimating their cost. But then building those upgrades into the models, repeating the analysis to confirm the constraints went away, or if they didn't, adding more upgrades until it does. It is an iterative computation process, as Ryan already indicated. And then also repeating this, not just for, alleviating constraints in one analysis, but if you're familiar with MISO's process, there's an energy resource study as well as a network resource study, and the NRIS analysis, the network resource study, follows the ERIS analysis, and it kind of starts with all of the upgrades from the ERIS analysis included. So once we do this iterative process for ERIS, we begin anew for NRIS and then iterate from there to alleviate all those constraints as well. So there is quite a lot going on under the hood. When we refer to sugar here, it's not just like a power flow, in the aggregate, I actually haven't done a count, but I don't know, probably many millions of individual power flow simulations, given all the contingencies and repeats to alleviate the constraints, test the upgrades and all that. And of course, at the end, a report gets spit out that is human readable, digestible, probably a bit overwhelming, especially for the larger cycles that have a lot of projects, a lot of constraints. So likely some usability improvements that could be made in the future, but that all comes together or comes out of the system as well. I won't get too deep into the weeds with the actual system architecture under the hood, but what I will say is that it's deployed on AWS. So this is the cloud-based software deployment. There's a user interface on the web that MISO logs into, and then under the hood, quite a lot going on just in terms of the data orchestration and data storage and versioning. We use a lot of AWS services, kind of off the shelf, as well as we've built a lot of our own orchestration tools. All of this deployed on Kubernetes to parallelize the many simulations that kind of go on concurrently. Inputs and outputs are versioned. They're stored on, well, depending on the file type, on S3, which is object storage, basically just files, or in databases. I could probably go on and on about this, or at least our compute engineering team could. The last thing I'll note before moving on is that, security is often a concern with critical energy infrastructure information, CEII in the cloud. So what I'll say is that, at Pearl Street, we've implemented a pretty rigorous security posture, including appropriate controls on storage and handling of CEII. That includes extensive logging, monitoring, alerting on our data and compute systems, but also general adoption of best practices around encryption, fine-grained access control, using principles of least privilege and the like, all things like that. We've undergone third-party penetration testing, an audit of our usage of open source software for security holes. We maintain a live dashboard of our infrastructure and those controls. So it's something that we take seriously, and also MISO takes seriously. It's a fun read to look through the security addendum to our contract, but it is quite extensive, and it's a critical piece of this system. So returning to some of the individual steps in that flow chart, beginning with the model building. So as Ryan noted, this is basically, you take your foundational transmission planning case, MTEP in MISO's case, and then you have to layer on a bunch of stuff in order to build the model that actually plugs into your power flow software to run the study. So from MTEP, add in any transmission upgrades that might be missing from that MTEP series. In the DPP studies, a lot of the times that's like the long range transmission plan, the LRTP projects. So those get layered in. Prior queued projects. So if we're talking about the 2023 model build, we'll need to layer in the 2022 projects that are active, that haven't withdrawn past the decision point. as well as 2021, 2020, basically anything that hasn't yet made it into MTEP. In certain cases, the upgrades carried by those projects also get added into the models. That's not always the case, but sometimes it is. So those have to be included as well. Then you add the current queued projects as they come out of the intake database. MISO uses an online submission system. So basically whatever data an interconnection customer added. But then there might be like project overrides or patches, basically for scenarios where what was submitted maybe doesn't represent the project richly enough, like with enough granularity, just due to limitations in the in the form. Or it could be things like, in what we're doing for MISO, we have sort of a separate input that defines when you add a project, excuse me, to a certain point of interconnection within a certain transmission owner at a certain kV level, it should be added to regulate like a certain voltage. So that's kind of another input that gets incorporated to construct the study model. And then once you create the power flow models, if you've ever run a power flow study, you know that you also have to update your con file, your sub file, basically these auxiliary files that indicate to the power flow software what contingencies are you running, and then what facilities do you care about for monitoring? So what constitutes a potential violation, and then what are all the subsystems for sourcing, syncing, or potentially for monitoring as well. So those get updated on the fly within the system. And then once everything is created, the resulting outputs are available for download by MISO, or they're just fed directly into the next stage of the flow, which I think, as Ryan noted, was in MISO's process, dispatching and solving the power flow models. We've made note of this a few times already, but MISO's queue is huge. These recent cycles have been very large. 2022 in particular, it's so much generation that from a modeling standpoint, given the way MISO does this, which is a fuel type dispatch, it's almost like displacing every existing generator in the footprint and replacing it with something from the queue. It's just a very large change to that underlying power flow model. That ordinarily is very difficult to solve. It's just a very large deviation, I would say, from the initial conditions of the model. So one feature of our software, I'd say what people primarily know us for, or at least knew us for maybe before this, was Sugar's ability to solve very challenging transmission planning cases. It's basically under the hood, it leverages kind of an optimization engine that we've built ourselves. We don't use any commercial solvers, so it's all kind of custom built for these very challenging transmission planning and interconnection problems. So given this very messed up and broken initial starting point for a power flow case, Sugar solves it with whatever degrees of freedom the transmission planner, kind of the user, allows. That can vary depending on the application, right? It could be anything from redispatching generation to adding reactive power support or new transmission paths. It could be load shedding, which, that in particular, not allowed for an interconnection study. But the point is that what Sugar is doing under the hood is it's kind of localizing and quantifying all of the imbalances in the system, both real and reactive, and then using that information to adjust resources or add resources given constraints set by the user. It's not a brute force approach. Like, it's not just looking at exploding Newton-Raphson iterations and then trying to, add an SVC here and take it away or something like that. It is much more holistic, but in the end, you get a solved power flow case and in a few minutes that's done automatically, rather than something that's more of a kind of like a back and forth, an interplay between an experienced transmission planner or study engineer and the software. I don't know if any of you were following kind of the earlier IPWG meetings from, I think, last summer. This is kind of where we had initially, MISO and Pearl Street had initially intended to deploy our software. and then things just kind of blossomed from there. But this is still a core component of what we do in helping MISO advance their process. So now moving on to, in the study, once you have your models set up, you can run the power flow analysis, right? And the idea is you're looking for constraints that you have to mitigate with upgrades. MISO developed, and I will say this is MISO, I mean, we work together collaboratively to think through this, but this is really MISO's process to basically define network upgrade selection based on sound engineering principles. Ryan could talk about this better than I can, but what I will say about this is that MISO really wanted to make this process as transparent as possible. So no sneaky black box magic tricks about how upgrades are selected. It should be easily, documented and shareable so that all the stakeholders in the process, whether that's an interconnection customer or a transmission owner or a consultant or whoever, can refer to that document and understand what the software is going to do to mitigate these different constraints. I've included a link in the slide to, I think it was the original IPWG posting. So hopefully that link lives on in the long term, but the white paper is available. I think it'll be a living document in the sense that we will make improvements, or MISO will make improvements that we will work with them to update. This was posted, I think, initially in January or something like that, and MISO got a bunch of feedback, which was incorporated, and that's probably always going to be true, right? I think we're sort of just getting started with what's with what's possible, and we'll make iterative improvements for there. But just to walk through like a very simple example of a line overload on like a 115 kV line, generally the way this process works is you run your power flow analysis, right? And if this is like an ERIS study, it's a contingency analysis, and you identify a line that is overloaded in a certain contingency. So what the software will try, based on that network upgrade white paper, is first reconductoring that line, basically upgrading it to a conductor that has a higher ampacity. Then, as we spoke about many times already, it's iterative. So we have to test that mitigation. Basically, we run the entire study all over again. So if that reconductor alleviated the overload, then we're done, or at least with this specific constraint, this specific mitigation. If it doesn't, like what you see on this slide, then we move on to the next available upgrade, which in this case is adding a new line, but not at the higher ampacity, kind of going back to something that is lower in its rating, and then evaluating new overloads and kind of continuing the mitigation process. So the one thing that I'll say here before moving on is that this process, it's not intended to gold plate MISO's system, right? It's designed to intelligently, at least, following this rule set, make kind of incremental upgrades, just what's needed to alleviate the constraint, not going wild with every possible constraint and overbuilding the system to an unnecessary degree. And the last thing about upgrades, and Ryan already pointed this out, but our software system is designed to not be the arbiter of like what is the best upgrade and what is not, right? It's designed to spit out these upgrades based on this rule set in a very transparent way, in something that's very, very quick. But one thing that automation affords, the broader community, whether those are interconnection customers or transmission owners, is just more time to pay attention to the constraints and the upgrades that really matter to them or make a difference. So if using the 2022 cycle as an example, there's something like, I don't know, 2,000 network upgrades or more that get spit out just because there's a lot of constraints, just given the size of that cluster. Maybe a bunch of those, the defaults are fine, like, you know, reconductoring or rebuilding a 69 kV line or 115 kV or whatever, but there's some very delicate upgrades involving like 500 kV system or 765 kV or whatever, that the transmission owners or the interconnection customers want to spend more of their time focusing. Like, they have the ability to do that, and then the software can take in alternatives, which you can do in one of two ways. So one, if you like our upgrade, but our cost estimate is not great, you know, or not, maybe not up to date, whether it's, you know, crossing a river, going through a swamp, or you know, something like that, you can supply basically that same upgrade, just supply alternative data. So that might be different costs. It could be different impedances for the lines, whatever. But that's sort of the simple replacement approach. But there's also an option to provide an IDEV to alleviate the constraints. So it could be, if you're not familiar with that acronym, sorry, IDV, industry standard format for kind of adding changes to power flow models. So you can upload, or sorry, in this case, send to MISO an IDEV file that includes an alternative upgrade that mitigates a subset of constraints, and then that gets provided as an input to the software, and it evaluates them. So if your upgrade successfully mitigates the constraints, great. You know, it could be included if it's lower cost or makes more sense. There's some opportunity to include grid enhancing technologies or alternative transmission technologies. Some of those are difficult to represent within a power flow model, like tower lifting. I don't think there's like an exact, and that's explicitly mentioned in Order 2023. You know, that doesn't have like a great power flow representation in and of itself, but things like testing various reactive devices, whether they're StatComs or SVCs or whatever, you know, those can be incorporated and run in the analysis to see if they mitigate the kind of the target constraints. So that is it for me. I'm going to turn it back over to Ryan, who will take over with some of the kind of the benchmarking work that MISO performed.
Yeah, thanks, David. So, yeah, I wanted to highlight at right before we kind of open it up for questions, just a couple of the benchmarking things that we did. So I would say we basically did I called two different benchmarks. You know, one was a benchmarking of the flows and constraints. So can we take an existing model and output from the previous cycle and phase one, and can we run that exact same model and whatnot through sugar and basically get similar enough results from a flow constraint problem, right? What are the transmission constraints? You know, when we started this, we put a kind of a benchmark for us of matching 98% of the results. And so we went through that benchmarking, and this benchmark report is available for folks to review. We saw a 99% constraint matching between what that older cycle that was complete and running it again through sugar. And so that was a really good result, right? We've got thermal analysis, the NRIS, and the voltage analysis. When you look at it, there's a very good matching of 99% constraints when you're benchmarking the flows and the constraints there. And so we want to, continue to look at this, and we're continuing to work on implementing sugar into to the process. But again, this benchmarking was a big part of ensuring us and giving us confidence that we've got good results here to go forward with our analysis. So that was basically can you get the constraints, right? The next part is basically the benchmarking of everything that we just talked about, from a network upgrade selection standpoint, right? We wanted to, of course, built that white paper. You want to kind of test, does that match similar to the results at a high level? And we've gone through a little more of the details on some of that benchmark on a high level into like breaking it down by areas and voltage classes and whatnot. But overall, very good, we think, matching on that. And so you've all probably seen this slide. So this is a slide that we produced. in one of the IPWGs, you know, and basically what we're showing here is when we did this benchmarking of that cost, we took up the 2021 South Phase 1 model, you ran that model, everything through Sugar, and used that white paper and that process to get the network upgrades and cost, and estimated that and compared it to what we got in the Phase 1 in the benchmark kind of case. You see here the costs were really close, right? 13.36 versus 13.25 at a high level. That's awesome. And then when you see the timing aspect here is just that this is where this is so exciting here is that, you know, when we look at the Phase 1 process, you know, when we did it before, it was about 668 days, that whole Phase 1. You know, Sugar, we did it in 10 days. So we got within 1% of that cost, and the run time is in 10 days. And, you know, we're continuing to improve on that run time here as we get through some of the implementation of this. So again, you know, we've got both those benchmarks. You know, we think, you know, we got the constraint mapping, all that reports out there available for view. And then we've got hey, we created a white paper, and, you know, I think we're going to be able to, of course, as David mentioned, it's a kind of a living document, right? That was the first step of kind of putting that out there, starting that, getting some transparency there and see how close we were. You know, I think we'll get some refinement of some of that over time, and we've already seen some places we could probably refine a little bit of that white paper to get a little bit better results there. But ultimately, this was a really, really good result, and so we're happy with where we're at with the benchmarking there. And with that, I think that brings us to just a summary of what we talked about today. So, you know, we've implemented a number of things over the last couple of years, and, you know, MISO feels, you know, thinks, you know, is an innovator, we think, in this space in the interconnection world. You know, we've done a lot of reforms over the years, over the decade, and, you know, this is just the latest implementation, you know, thing that we're implementing to really get us down to that 1-year timeline, right? We made a tariff change that we wanted to get this down from application, submittal, and approval to the GIA in 1 year. And so having automation in the ProStreet software is a big part of being able to meet that timeline. You know, and we need to get this, you know, before, as I didn't even mention at the beginning, is just some of the Order 2023 penalty structure, right? We need to do this, and we need to get it done in that timeline to avoid those penalties. And so we're really hopeful, and we're really happy that we're seeing some fruits of that labor already in the implementation and get the timeline into a 1 year. So again, it's that from kickoff results are going to bring all that time and all that transparency, we think, from a network upgrade deployment perspective. You know, and again, we're going to continue to provide additional capabilities and enhancements. You saw some of those pieces there were like the model building aspect, which is a big piece that I don't think we've seen yet in some of the, like, again, in the 2022, but we're going to see some fruits of that labor in the later in cycles 23 and beyond. And so, you know, we're really excited again to continue to work with ProStreet to achieve that 1 year timeline, and looking forward to getting through the backlog. And with that, unless David, you have any other summarizing thoughts before we open it up for the Q&A?
Just one last note, particularly for any of the MISO interconnection customers attending. Just wanted to say thank you for all the feedback that's been relayed via MISO and your general engagement, I think, in the process as we get this, or as we get everything spinning up. I once heard somebody from Southwest Power Pool make an analogy that implementing interconnection process improvements is like building a car while trying to drive it. And honestly, it's a pretty apt analogy. But it's an investment that, you know, that'll bear fruit. And I just wanted to say thank you for coming along for the ride.
All right, thank you, Ryan and David. We have lots of questions and not nearly enough time to get through all of those. So like we do for most of these webinars, any questions that we don't get through during this hour, we will pass on to the speakers and they will write out some of the responses, and we'll try to get that out to all attendees, perhaps by the end of the month. All right. So one question here, and I think you already touched on it, on some of the time savings that you're going to be seeing, right? Going from multiple hundreds of days to 1 year. And in your example, really doing a lot of this in just a couple of days. What does that extra time get you? On the one hand, you are just catching up, right? But what do you do with all that extra time? Is it more in-depth analysis? Is it scenario planning? Is it deeper dive into the solutions and the network upgrades? What do you do with that time?
Yeah, that's a good question, James. I think ultimately, we need this to get the working on the backlog, right? We need to move through that back, like I mentioned at the beginning, 300 gigawatts, right, of that. So getting through that is helpful in implementing this automation. And then even like the long term, right, getting to that 1 year time frame. Without this, that doesn't happen. And so I think where you focus, I think what this helps focus on is, not just in, phase 1, 2, and 3, but just on the mitigation selection. That is the most time consuming part of the process, no doubt, right? And especially when you have a cycle with 140 gigawatts, you have thousands of constraints, right? And so what this tool really gets you where you can spend time is focusing in on the network upgrades that are truly need to be looked at, right? I've been saying, a big majority of the ones that are, the white paper is designed to do should be a no-brainer, right? I put a new conductor size in. Okay, great. And then so our hope is that time that we have is not focused on, the thousands of them, but can be focused in on the really problem network upgrade, areas where you might need a little bit more time and engineer look at the system, right? That, hey, does this thing go across the river? Can you do something else that we couldn't program in because, we don't have the data that would be available to even make a decision on that stuff. And so I think that's where, some more of the time is going to be more focused in on the actual problem areas that we really do need to spend the time on, and not spend the time on, network upgrade selection and cost that are really, they're fine. Let's go spend time on ones that really need to.
All right, thanks, Ryan. So there's a couple of questions here on process, on the results, on data. So we'll try and cover as many of those categories as possible. So you just mentioned the different phases of the GI study and the GI process. And right now you're employing Sugar for phase 1. Could you talk us why just phase 1? And is there a plan to do it for phase 2 and phase 3?
Yeah, that's a great question. So why phase 1? Phase one is the longest phase, right? Because you have so much volume in there. So you have to do it in there. You got it, and really the phase 1 is where the most drop-offs happen. So having to look at the phase 1 of more of a kind of a feasibility study, right? Hey, can you really integrate 140 gigawatts? Sure, but it's going to cost you 100 billion. So you got to make some decisions there on that. And so that's why we're starting in phase 1. It's the longest phase. It's got the most amount of constraints. It's got the most dropouts, right? And so getting the automation of that keyed in is important to basically achieving the 1 year time frame. Without getting the phase 1 done, there's no way, right? You got to get that one down into the point of getting through that in a reasonable time frame. For the future, we don't have direct plans like today to move this into later phases. We're still focused on getting it implemented for phase 1, right? We've got a couple aspects that we're working on that have, right, in for the future cycles in terms of model building, right? And then even the QA, QC parts that you saw on that slide there. So there's some phases here that still have to be built out and put into the workflow for the next cycle. So we're really focused in on phase 1 at this point. At some point, right, when people get more comfortable, right, this is the first rollout with this, there may be opportunities that we do use sugar in more parts of the process in the future.
Thanks, Ryan. Two more questions on process before we go to results and validation. Even if I hadn't teed this up at the very beginning, the question was bound to come up. Can sugar be used for large load interconnection? And implicit in that question is how similar or dissimilar is a process for generation interconnection and large load interconnection?
How, David, is that more of a, is that, you think that's more of a technical question? Could it be used to do that, or is there a process that we could use? How would you take that, James?
I can answer from at least a technical perspective. I mean, all I would say is that a steady state transmission planning study that involves putting together power flow models, setting them up for a study, dispatching, solving, et cetera, running analysis, identifying upgrades or constraints, upgrades, costs, whatever. Whether that's for generation or load, or even if it's just like some random scenario for a long-term policy study, yes, that can be done in sugar. Yes, it can be automated. We have not explored like load interconnection studies with anybody at this point, MISO or otherwise. If it's something that's on your mind and you want to talk about it, happy to. But yeah, I think from a technical perspective, yes, but we're not currently doing that today.
All right, thanks. Another question here. I'll read it as is and add some. So cost allocation automation could easily be implemented with the existing tools. Why did MISO choose to switch to an entirely new solver to solve that step? So part of that question I'm taking as is the unique thing about this process and the deployment of sugar really that cost allocation automation, or is there more to it? And what's unique about this new process that could not be done previously?
I'll start, and I don't know if you want to add, David, but I mean, the way I would say is, we knew that Pearl Street was working with other entities at RTOs on some parts and pieces of sugar, and we've been in discussions with them over time, right? And just what kind of aspects could help piece some of this and help with our process. And I think David said a little bit about this at the in his presentation. Part of the presentation is, this all started like we got the 2022 model, and we had we were building 170 gigawatt new resources in this system, and it was all done by hand, right? And it took, I remember, it was weeks and months to just put generation into the model and get it to solve, right? With 170 gigawatts on a system that had a peak load of, it's roughly 130 gigawatts, right? That's very, very challenging. And so where this kind of all started, and David said, it was like, can we model build and solve this more automated and better, right? And that's where it really started, right? Is, that's why we're in, is the model building aspect of that and the solving aspect, right? We had the 2022 model and large queues that's going to be challenging to do that. So then from that, we kind of, we had a lot of other aspects of that we did want to implement as part of the automation and making all that work from, getting applications from the portal all the way through, solving power flow network upgrade and then system impact study. The big important piece, and I think, the question, about the cost allocation, sure, could that be implemented? And I think actually Tara already did, but we built that white paper in front of everybody out for public review and everything. And so, yeah, that's available, and yes, that's a big piece, I think, of the automation here that is good, is kind of bringing that transparency, bringing that, it's repeatable, right? This is how it's done. Here's the workflow, how it does, and that's out there for everybody to review and be able to bring that transparency. And so ultimately, yeah, could you implement that in somewhere else? Sure, but that was developed as part of our stakeholder process and for folks.
If I can just add a couple more comments. So, honestly, we try not to be dogmatic about how our software or automation solutions are applied or not applied. Like what you've seen today is kind of an end-to-end process that MISO has elected to deploy. And I'll come back to that in a second, but we've had a very fruitful and successful partnership with SPP now for like 3 years, literally just for the model automation piece. And the outputs of our software, basically those solved power flow models, they're run in other power flow tools by SPP engineers, by consultants, et cetera. Like that's totally valid. And we're like when we work with a transmission provider, we don't tell them you must use our software for all the steps. It's like what is your bottleneck? What are you trying to solve? And then we kind of work together to figure out what the appropriate solution is. But I think with MISO, and I don't want to put words in anybody's mouth, certainly, but I think general recognition in kind of the opportunity of what end-to-end automation could enable just in reducing overall time and opportunities for error that come with like data handoffs between different people, different teams, different organizations, and things that are like quasi-automated or quasi-manual with like in some cases patchwork solutions developed by different people and different organizations over time. I'm not saying the cost allocation automation is like that specifically, but just the process overall. And honestly, like it's good to automate individual step bottlenecks that you have, but there's a lot to be gained just by automating the entire process end to end, particularly once you get it all up and running. And I think that's where we went together. And there's more to be done, to be sure, but I don't think that again, we don't tell you that you have to replace a power flow engine or whatever if we're working with some RTO. There's benefits of doing it for that end-to-end process, but we're certainly not claiming that sugar is the only engine that could do every single step of that process, but we can certainly do them all, and I think in a very compelling way.
Great. Thank you, David and Ryan. One last question before we wrap up, which has come up a couple of different times in Slido, is looking at validation of results. So that's what you ended on with the benchmarking. Now that you are in kind of production phase, as you find discrepancies between the results that you're coming up with this new process compared to how you traditionally have done it, what does that process look like for figuring out what the solution is, right?
Yeah.
There are discrepancies where there are differences.
That's a great question. So, the good thing is we aren't doing anything that much different from that standpoint, right? We always post raw results even before whatever tool you use for feedback and review. So we take that feedback. If there's errors or there's things that need to be or questions, there's opportunity for that feedback. We've done that since I've been in the queue. That's a big important piece of all this. So if there are things in these models or XYZ that need to be looked at, we look at them, right? And so, even in this process we're doing right now with the 2022, model's been posted in some form for 2 years, right? And this is 2022 cycle, right? We've got raw results that are posted at least twice, once in February, March. We've gotten feedback through that. And then also, recently the draft system impact study, right, that we posted last week that we continue to get feedback on, and we're reviewing that feedback. So, the good thing is I don't think anything's changed. We've always accepted feedback in all these in this process and willing to take that feedback and take that and change things if there are errors, fix errors, or even take alternative mitigations as part of that process. So. Again, the good thing is I don't think that's changed much since we started the queue.
I will very quickly add, because I know we're at time, like the benchmarking exercise and that paper Ryan referred to, it did indicate some like known differences between our, like Tara, which is MISO's current software that's used in DPP studies, and Sugar. Some of those differences are explainable, like slightly different implementations of like a DC screen, AC verification, etc. But in general, like the point that I would try to convey is that this is MISO's process, right? I mean, they own it and it's defined pretty explicitly. Maybe parts of it could be better in the business practice manual. Like Pearl Street doesn't own it. No other software provider necessarily owns it. We're all just trying to implement the same thing. And I mean, we've been working pretty closely with MISO to ensure that our implementation kind of corresponds to their process, their understanding of the process, the BPM, et cetera. And I think, as Ryan said, as any issues are identified, like we try to resolve them pretty quickly. And I mean, as MISO changes its process, we'll be right alongside with them, you know, implementing that. So just thought I'd make that point.
Great. Thanks, David. Thank you, Ryan. So we are a minute over, but that's because we got a ton of questions, a lot of interest in this topic. So I really want to thank you, Ryan and David, for taking the time to give this really informative presentation. There are a couple of questions. People wanted a little bit more details, and I would encourage you to reach out to Ryan and David specifically on some of those topics with the contracting and such, and they'll be able to walk you through that. Again, we appreciate your engagement, everyone that's dialed in and stayed on this long. We will be sending out an email with a link to the presentation and answers to the questions that we did not get through. Again, Ryan, David, thank you so much for joining us, and we hope that you'll be able to join us again.
All right, thanks for having us. Thanks, everyone.
Bye.